Okay, well, hello everyone. Thank you all for joining us today for the next wave, Driving Wireless Innovation with Spectrum and RF Solutions, where we will cover global spectrum updates, radio architectures evolution, and RF front-end innovation. This webinar is hosted by pSemi Murata Company. pSemi, formerly Peregrine Semiconductor, is a leader in the design and development of semiconductor integration, providing world-class capabilities with high-performance RF analog and mixed signal solutions. With a 30-year legacy of technology advancements, strong IP portfolio, and deep expertise in RF integration, our solution portfolio spans power management, connected sensors, antenna tuning, and RF front ends, which enable advanced modules for smartphones, base stations, personal computers, electric vehicles, data centers, IoT devices, healthcare, and more. pSemi is headquartered in San Diego with additional offices spanning North America, Europe, and Asia. Today, we're joined by two industry experts from pSemi, Rui Ma and Peter Bacon. Rui Ma is Millimeter PA Systems Director at pSemi. Dr. Ma was a Senior Principal Scientist of RF Research with Mitsubishi Electric Research Laboratories in Cambridge, Massachusetts, where he received a MIPI Alliance Award for his contributions to the development of the analog reference interface for the eTrack envelope tracking specification and top corporate R&D awards for GaN development and its RF applications. He's also a senior member of IEEE and inventor and co-inventor of more than 30 U.S. patents and patent applications on RF-related topics. Peter Bacon is Senior Director of Systems and Application Engineering at pSemi, where he oversees system and standards analysis, product requirements, definition, and application support. Peter has over 35 years of RF and millimeter wave integrated product development experience gained from his career in this field. If there are any questions throughout the webinar, please type them in the chat and choose to send them to all panelists. There will be a time at the end to go through all of the questions. I will now hand it off to Peter to dive into the presentation.
All right, thank you, Madison. So to start off with, there'll be roughly four different topics that we'll get into: spectrum update, then we'll get into the RF radio architectures, then the implications for the RF front end, and then come to a summary at the end. So looking at the spectrum update, WRC 23 will cover that as well as what's being focused on for WRC 27. We'll take an in-depth look at the IMT spectrum for the US for the 7 gigahertz. And then a topic that's gaining a lot of interest is the increased spectrum sharing. So with regard to spectrum regulatory bodies, there are basically three different groups: global, national, and standards. And within the global, we have the ITU, the International Telecommunications Union. This is part of the United Nations. It addresses the information and communication technologies. And within ITUR is the radio communication sector of ITU. So it convenes on a 4-year cycle to have these World Radio Communication Conferences. So the next one is scheduled for 2027. The most recent was in December of 2023. Within that, countries submit their views on different portions of spectrum. And what is shown here on the two plots on the right is sort of a consolidation of interest, either by the ITU region, 1, 2, or 3, or by major country, and I've listed them here. And so there's quite a bit of commonality, but there are also some very distinct areas of spectrum that stand out as being different depending on where you are in the globe. So some of these spectrum sections have already been used for IMT, and that'll be our focus for today: international mobile telecommunications, anything that's used for cellular type applications. And so presently the 700 to 900 megahertz is already being used quite dominantly across the globe, and you can see that in the charts over here. And then 2500 to 2690, that's also a very common band in the US and China and elsewhere. So that's got a lot of activity already for IMT. And there are many that are being used as well. The 3400 to 3800 very much in the European spectrum. There's quite a bit of activity there, but the emphasis within WRC 23 was to get more global harmonization for that. And then finally, there are other portions of spectrum that need further study before signing them up for IMT. So 4400 to 4800 and also 14.8 to 15.35 gigahertz. Some of this is already used for IMT, as I mentioned, but it's again pushing it towards a more global recognition for use for IMT. Within WRC 23, there were resolutions that came from the meeting, so basically decisions and agreement. And then there are WRC 27 agenda items, things that will be worked on over the course of the next 3.5, 4 years. So within this, there was one resolution that did define those agenda items, and agenda item 1.7, we'll spend some time on this. It focused on three major spectrum regions, I'm going to call 4.4, the 7.1, and the 14.8 gigahertz range. These are all going to be looked at in detail from a technical point of view, as well as interference with other existing services, whether in-band or adjacent. And then from that, there'll be conclusions that'll show up at the WRC 27. So some resolutions, these portions of spectrum were agreed to be used for IMT generally across the globe. There are some restrictions in some cases. And then study items, as I mentioned, AI 1.7 being a dominant one, looking at these three portions of spectrum. Within the 1.7 agenda item, the ITUR called on Working Party 5D. That's the working party that does all of the detailed analysis for IMT-related studies. They meet quarterly, next one coming up tomorrow, starting tomorrow. They've already started collecting input from other organizations, and one example is 3GPP. They provided a request into 3GPP for parameters, system-level parameters that address the radio detail as well as antenna and total system implementation. And 3GPP has responded through its working group RAN 4. RAN 4 has already provided two liaison statements, one just in the, I want to say the August timeframe, the August timeframe from the RAN 112 meeting, and I believe also in the earlier part of the year, Q2 of the year. These two documents that describe the parameters, the first one being for the 4.4 gigahertz and the second one being for the 7.1. And they're presently working on the third set of parameters for the 14 gigahertz. So we focused on WRC and getting to a global understanding of IMT spectrum, but there are differences as we look at the regions. I just want to highlight a few of those because ultimately the national level is what drives specific regulations in the country. So within Region 1, European CEPT has its view on the 7.1 to 8.4 gigahertz. They want to protect right next to this band the Earth exploration satellite services and also the sea service temperature capability that is presently in this space. So they're protecting that operation, so they'll probably have an impact on what they look at for the 7.1 to 8.4 gigahertz range. So they are considering portions of that spectrum, but again, concerned about the coexistence and the adjacent spurious concerns. And then Russia wants to also maintain its space operation services that are right next to and overlapping some of the spectrum that's being considered. In Region 2, a big difference in the US is that it's allocated all of the spectrum from 5.9 to 7.1 gigahertz as unlicensed for Wi-Fi, but they are investigating the 7.1 to 8.4 gigahertz, and I'll get into that in more detail. They've also requested the 3.1 and the 12.7 gigahertz studies be part of the WRC 27 agenda, but to my understanding that the ITU has not agreed to that at this point. And then in China, their regulatory body, the MIIT, has already indicated that they're looking at the lower portion of the 6 gigahertz spectrum for IMT, and they're supporting all of the activity related to the higher portion of the 6 gigahertz for IMT. And they're also supporting right up to the 7.1 for IMT globally. So as we look at what came out of WRC 23, we have some resolutions, decisions on this spectrum. They're doing study items for WRC 27 on these 3 portions. And yet we see differences that occur at the country level. And IMT assessments are being requested and being done, in fact, within the US for these different portions of spectrum, and 13 gigahertz being one. That stands out as being fairly unique to the US. And then unlicensed was also a big difference between the way the rest of the world is looking, whereas in China, that's all being considered for IMT. And that was also agreed to be at least a portion of it from a WRC perspective. When we take a deep dive into the US and specifically the 125 to 8400 megahertz spectrum, the challenge there is there are a number of incumbents and licenses already in this spectrum. There are 8,700 assignments, and there are over 7 mission critical uses within the spectrum listed here. And you can see visually from the spectrum point of view how they align in terms of where they're located. Fixed services has allocation across the entire band, and then also several bands are presently shared. So with space terminals and with ground and maritime terminals, and shown down in the lower 2 bar graphs here. So it's a very challenging piece of spectrum for the US to try and pull some additional IMT spectrum from. When we talk about spectrum, one key thing that is also being looked at as we look at 6G and how do we make the best usage of the spectrum that is available is talking about spectral efficiency. And when we talk about spectral efficiency, you see how it's defined. You have the number of bits over time, over frequency, and over area. And also using Shannon's law, you get a sense of how we could maximize total capacity for a given spectrum. Some things that stand out, SNR, as we increase the SNR, meaning the signal quality improves, we can cram more bits into each symbol that's transmitted and therefore increase the spectral efficiency that way. Then also the number of antennas, number of MIMO distinct uncorrelated channels helps us to expand that. So you see that going on very dramatically in a lot of the Wi-Fi access points. And then most obvious is the spectrum itself. You add more spectrum to it, you can increase the capacity directly. Some other concepts in terms of area, as we look at spatial multiplexing, we can divide the space that a base station covers. Historically, base stations have been sectorized into 3 sectors, and therefore that gives you some spatial separation and allows you to have greater number of users in a particular area. With multi-user MIMO, the beamforming now becomes even more integral, and you can pinpoint a beam towards a user far more greatly with greater directivity of the beam itself. And therefore you can increase the effective number of beams that any base station will have, even in a sectorized configuration. And then finally, densification. You reduce the area covered by each base station and increase the number deployed. So you get to, again, a smaller area per base station and divide spatially the spectrum for a geographical area. The second point is more having to do with time. That spectrum utilization is often a limiting factor. So quite often there are many licensed incumbents that use the spectrum at a very low percentage. And that could be like a geographical related, meaning you've got many users, but over a wide area, and they sort of clog up a nice clean spectrum. We've seen that with the BRS, EBS licenses within the US in the 2.5 gigahertz range. And then you can also have a time and geographical related dependency. And the naval radio location, so radar in this frequency range, the CBRS band, that's only an issue when ships are actually in port and also along the coast. So there's a very limited restriction there. So there's a great reuse of the spectrum presently in the CBRS band. So spectrum sharing between diverse users and systems is needed to increase the spectrum utilization and total capacity. So when we look at spectrum sharing, two examples. One is the CBRS example just mentioned. So the dominant priority incumbent access license is given to the federal use, so very much maintaining the radar capability. But then there are two other tiers that are part of the licensing scheme. One is priority access, and that's for IMT usage. And then there's tier 3, which is the general authorized access. All of the tier access is controlled by a spectrum access system. So this has been new, added part of the CBRS implementation, and it controls the spectrum access per the licensing schema. And then another thing that we are seeing more and more is the dual use of spectrum. And so this is an example of Globalstar reusing its already existing licenses in the mobile satellite service spectrum, 2483 to 2495, but they're leveraging it by implementing what they call a ancillary terrestrial component. So basically leveraging base stations to help them maintain and improve the overall coverage that they have. So whereas the service link might have some limitations on throughput, you can improve that with a more localized capability, and also just improve the overall flexibility of the network itself. So employing an IMT piece within the MSS spectrum. And then finally, in terms of spectrum sharing within the US, the NTIA, the National Telecommunications and Information Administration, issued the National Spectrum Strategy this past fall. And with that, they've included what they call a moonshot action plan on spectrum sharing, and focusing on the US spectrum of 3.1 to 3.45, they want industry to provide new models of how to share spectrum. And along with proposals, they're also asking for demonstrations of that. So that'll be going on over the next year, 2 years. And the sharing models are likely to combine several of the following tools here. Basically a database with policy management, similar to the what was shown in the CBRS. More cognitive radio spectrum sensing, so you, from a handset or a CPE device, you understand and determine what's going on around you. And then more at the network level, determining what's happening in the surrounding environment and adjusting the network and spectrum access based on that. And of course, AI, ML assisted dynamic frequency selection. So both for throughput, maximizing throughput, as well as identifying and optimizing what spectrum you're leveraging, given all the constraints and all the users that are detected. So with that, question then becomes, with all this additional spectrum, what happens to the RF front-end architecture? What are the implications to accessing the additional spectrum? And with that, I'll pass that on to Rui.
Thank you very much, Peter. Let me take over the So next, I'd like to share some of the innovations happening on the RF front end, given the spectrum situation Peter has mentioned before. In this section, I will cover both the base station and the UE aspect. So first, as we know, the massive MIMO has been the enabling technologies for 5G. So what's going to happen on the 5G advanced and also upcoming 6G is the further increase of the massive MIMO numbers in terms of active antenna channels. And this has a big implication on the base station side. So why do we need a more number of TX, RX numbers, which is actually providing a more capacities? So Peter has mentioned that the network capacity has been one of key focus of moving from 5G to 6G. Of course, there are also other visions provided by IMT 2030 has outlined the sustainability has also been one of the key factors, KPIs that the engineering community has to focus or bring up this new 6G generations. So that means a new innovative technology is really needed that has to revolutionize or further improve the radio technology at both base station and the UE side. Otherwise, the network capacities, given the predicting trend, is going to be really challenging situation. So let's take a look at what are the KPIs from 5G to 6G. So certainly, as users, as the mobile users, we are expecting experience further increase the data rate, but not only the data rate, but also the energy efficiency, both at the battery side for the UE as well as the infrastructure side, since this has a lot of implications on the environmental as well as the total cost ownership for the operators. So on the right side, actually we listed the different frequencies and that in different frequency we have different implications on the radio front end design. So for example, the lower frequency, they have much better coverage, but now often you have very limited spectrum available. So on the other hand, the FR2 frequency, we have quite a significant chunk of spectrum available. However, since they are at a higher frequency, often you have limited coverage. So one of the frequencies, the so-called FR3, in between FR1 and FR2, seems to offer a pretty good trade-off in terms of the coverage and the bandwidth. Therefore, it also has new implications on the front end design that I will also dive into in the later slides. So as mentioned before, the massive MIMO has really revolutionized the 5G, but how can we further continue the massive MIMO development into 6G? There are different ways we can further increase the number of massive MIMO. For example, we can increase the analog front-end processing, and also increase the digital front-end processing. Also, the beamforming, new beamforming algorithms can also be developed at a baseband. And therefore, this actually also implies that high performance R front end hardware and advanced signal processing algorithms, as well as not only the active component but also the passive filters and antenna design are needed for the new 6G development. So talking about the UE first, the FR3 in between 7 to 24 gigahertz as a very high level spectrum. Certainly we can also divide this into 7 to 10 gigahertz and also the 13 to 24 gigahertz. What we have seen in the industry based on the discussion, it more looks like the first focus will be on the lower spectrums due to the hardware development cycles and challenges. On the UE side, when we discuss of the UE architecture, one of the key limitations or factors is certainly the mobile phone size limitations. There are normally at high level we have FR1 like architecture and FR2 like architecture. FR2 meaning the millimeter wave above 24 gigahertz. On the FR1 like sub 6 gigahertz, is often we use the multiple antennas and for MIMO and diversity. In this configuration, the antenna are located at different locations and they are not correlated and also not coherent. On the other hand, on the FR2 like architectures, different type of beamforming, including digital beamforming and analog beamforming, are needed to form the beams. And this becomes very challenging given the handset limitations. Therefore, most likely for the 7 to 10 gigahertz, the handset UE will further follow a current existing FR1 like, but with increased number of TRX channels. And even also for the 13 and 15 gigahertz, this FR3 band, we would also most likely expect the similar architectures as FR1. Given the reason of the handset form factor limitations, it is pretty challenging to form the array if we implement at this 13 to 15 gigahertz for handset applications. So We also need to look at the different ways to increase cell capacity and as well as the spectrum efficiency. And this chart on the left side basically shows when we increase the spectrum bandwidth as well as the TRX numbers, we can get a 20x or even further increase of the capacities. And on the right side, we also need to increase the spectrum efficiency. If we go further based on the existing massive MIMO architectures, we increase the active channel numbers and antenna array elements, AE meaning antenna array element numbers from the existing 32T, 32R architectures to further maybe 128 or even further 500 TRX numbers. This has a significant impact on the spectrum efficiency on the base station side. On top of that, if we need a further double the spectrum efficiency, we also need the increase the UE in the architecture. Therefore, in summary, the wider bandwidth will move from sub-6 to the FR3. We are gaining wider bandwidth and also increasing the more TRX channel numbers. And this also implies the larger active antenna arrays is needed. And by combining all these technologies, and we can further increase the spectrum efficiencies. One of the hardware or practical limitations for the operators to deploy any new generations of base station is to consider the reuse of the existing infrastructure. One of the key limiting factors is the intersect distance. So what is the performance at this new frequency, the FR3 lag? According to some simulation and studies, it shows that given the existing sub-6 deployment, and it is possible to achieve similar SNR at this new frequency FR3 lag. Therefore, it shows the feasibilities of reusing, for example, reusing the urban rooftop sites for a FR3 band. So this is very promising results for FR3 deployment. But this is provided that we have some new innovation and evolutions happening on the architecture of the larger antenna arrays. So give an example of today's working house or one of the very globally deployed bands, 3.5 gigahertz, where you often have 32 TR, 64 TRX numbers, and the active antenna, and actually the antenna elements numbers is the sub-array numbers. Normally you have 3 sub-arrays where you have the radiating elements. Let's see, we choose the number of 192. And if we double the frequency and given the half lambda spacing, so if we do not increase the active channels, then certainly the size will shrink. However, given the higher frequency challenge of the path loss and other limitations, it is pretty challenging to have the similar coverage using the existing active antenna numbers. Therefore, luckily, or fortunately, if we can, given the array panel size, therefore, which is actually related with the installation challenge and the wind load and all these practical limitations, if we keep the same size as the existing 3.5 gigahertz and we double the frequency, actually in X and Y dimensions, we can put double of the active antenna numbers. Therefore, the total active antenna numbers is 4 times of the existing 3.5 gigahertz numbers. So this actually offers a very positive forward-looking of deployment at 7 gigahertz. And if we can also follow the same idea, follow the same trend, if we further double the frequency, let's say to 14 gigahertz, then we can also fit more active antennas and active channels in the same size. That offer you the compensate the higher frequency path loss at this FR3 new band. And because this will offer a newer, higher beamforming gain at this with more active antenna numbers. And this is a study from Ericsson, basically comparing the I will not go to the details, but you can take a look at this centimeter wave FR3 band and what is going to happen how are we going to, there are different ways, how are we going to implement more active antenna channels given the practical limitations of array size. So in a high level, we can increase the sub-array size by introducing more active antenna channels, but certainly we can also increase more real TRX ports. However, this all comes with associated challenge. A more practical approach would be a balance between this real increase of passive numbers and the increase of TRX ports. Therefore, the careful considerations is really needed to strike a good balance between the complexity and the flexibilities in both the baseband power consumption and resource, as well as RF and analog power consumption and hardware complexities. When we move to the higher frequency, certainly we are facing also other challenge. This including higher path loss at higher frequency, and also, for example, another challenge is the power amplifier tends to have offering a degraded performance and efficiency at higher frequency. This would also translate the thermal management and the packaging challenge if we increase to the newer frequency as comparing with FR1. So this would also actually demand the RF engineers to come up with more high performance at higher frequency, a more integrated approach which seems to really needed to resolve this challenge. So talking about the beamforming architectures, there are different ways we can do beamforming. For example, we can do the full digital beamforming, and where basically the beamforming is processed in the baseband, or we can do analog beamforming, where you basically use an analog phase shifters or phase shifting elements to form the beam. However, this has a limitations in terms of the flexibilities. The more practical approach currently would be a hybrid beamforming, where you, depending on the active streams you are forming, and this would also strike a good balance of the flexibility and the hardware cost and the complexities. This table basically summarizes or compares the different ways of doing beamforming, of analog beamforming and the baseband digital beamforming, and also the hybrid beamforming. The takeaway message is the hybrid beamforming offers a good trade-off between the digital beamforming and analog beamforming in terms of the complexity and flexibilities. Even talking about hybrid beamforming, we have also different flavors of doing that. One category we call it a beamforming. For example, you can implement the beamforming functionalities after the high power amplifiers. Therefore, you do not need a beamforming element for each of the PA. Therefore, you reduce the PA numbers needed, and this would offer normally a very popular deployment at a sub-6 GHz. However, it has unique challenge if we move to a higher frequency. The performance of these phase shifters or switches is very challenging in terms of the insertion loss and the power handling capabilities moving to higher frequency. Therefore, another different way of performing a hybrid beamforming would be to move the beamforming elements ahead of the PA. Therefore, it's really analog or insertion loss is less critical compared with the post-PA forming. So the spectrum, the bottom line is the spectrum characteristics depending on which frequency you are working, whether it's low or high, and what is the real practical challenge of implementing all these beamformings would finally have a deciding factors of the final solution, which way to go. Cost-effective and highly integration is becoming a necessary factors for FR3 solutions. So I mentioned many times about the integration, and this slide basically shows some examples offered by pSemi and Murata companies of our existing FR2 front-end implementations, where the antenna A module, the antenna in module is actually offered as a highly integrated solution to do beamforming at FR2 solution at the FR2 frequency. So where we integrate multiple dies and chips, which, for example, forming the beamforming elements as well as the up-down converters in a very compact form factors to offering of high integration and high functionalities with optimized system level performance. So in this section, I will talk about more on our front-end solutions. What are the new ideas, new technologies the research community and the industry has been looking at? So existing network is still uplink limited. Therefore, that means the UE capabilities and has been even in the 3GPP discussion and other research community, we have been focusing on improving the UE uplink capability because the current network is more or less uplink limited. The UE also has very complicated architectures when we have to integrate more frequency, more bands, more C combinations. Therefore, the integration approach with higher performance, analog performance front end is really necessary. And also the power amplifier front end of PA modules and the fan modules has a very key limiting factors or key performance indications on the overall energy consumptions and also battery lives. So therefore, to improve the performance efficiency for power amplifier has been a long research topics also in the industry and academia. In this talk, I will also highlight briefly some of the key architectures we've been looking at, including advanced Doherty amplifiers, switch mode PA, load modulation balanced PA, and the digital envelope tracking. So the Doherty PA has been the working house for the base station applications because it's relatively high performance and relatively simple architectures or relatively simple implementations. However, we know for Doherty PAs to implement the classical Doherty amplifiers at the handset is facing multiple challenge. One of the key challenge would be the size limitation. How designer can implement the, for example, the quarter wave transformers in the handset becomes a key challenge. In this work, you can look at the reference here. Murata has been looking at how to shrink the size of bringing the Doherty architectures into a handset applications. As the end of results, we are able to integrate the Doherty PA modules into a very 2.6 and 2.2 millimeter squares using innovative combiner networks where a high performance has been achieved without trading off too much of the size. So the testing results showing this source converter Doherty amplifiers is able to achieve a pretty wide bandwidth covering N40 and N41 from 2.2 to 2.7 gigahertz, offering a 35% average power additive efficiency while meeting the minus 35 ACP result. And the average power is also mentioned here. And okay, Doherty amplifier has not only has a bandwidth limitation, but also has other limitations because the way you bias amplifier, and also it has implications on the linearity perspective, as well as the VSWR immunities. So, and another way of improving the Doherty PA architecture is to increase, to bring in the dynamic biasing to increase its linearity. However, this work is basically focusing on top of that of how to increase the VSWR for handset applications of Doherty architectures. by this adaptive bias property, we can also take into consideration the VSWR variation of the new reconfigurable Doherty architectures. So that actually improves significantly the Doherty practical linearity on the load variation, even without a DBD. Another architectures, Doherty is also limited by how wide band of RF carrier frequency it can operate. On the contrary, the load modulation balance has the advantage of offering the over a much wider bandwidth of RF carrier frequency. But its limitation again for handset is the size and form factors. And Murat has also looked at this load modulation balance strategy of enhancing its performance given the size limitations. As a research or as we published this research at IMS 2023, it shows a very promising over a much wider RF carrier frequency from 3.3 to almost 5 gigahertz with a top class efficiency and linearities. So also the switch mode PAs has been another new high peak efficiency candidates for handset application. Classical class E would also suffering several limitations, including the harmonic suppressions. So in this new concept from Murata reported in the European microwave, we can also resolve the harmonic suppression issues and also using this differential common mode clock as well as the transmission line transformers to bring this high efficiency solution for handset applications again. So the measured results really shows at 4.8 volt, we are operating at a much wider frequency from almost 3.15 to 5.3 gigahertz with much higher improved efficiencies due to the switch mode nature of the PAs, and also with a very good agreement between measurement and simulation. So different type of envelope tracking has been studied. The classical analog envelope tracking is theoretically or in practical limitation also limited by the bandwidth, how wide the envelope tracking can handle. As if you do the studies, 100 megahertz over that is become pretty challenging to be handled with analog envelope tracking. However, we also explored the digital envelope tracking, which is a different ways of doing envelope tracking. It has its unique benefits, including the digital envelope tracking can handle much wider bandwidth of signal and can also support simultaneously multiple PA operation and also immune to the can sustain a much longer distance between the PMIC and the PA modules. And this is all benefits and the features that we needed when we moved to the new frequency range, including the FR3 and including some of the Wi-Fi applications for both mobiles, UE applications, as well as base station applications. So here we highlight the energy savings using the digital envelope tracking. It offers roughly between 20 to 30% of energy savings over a 200 megahertz of bandwidth, which is very attractive solutions. And also for multiple PAs and a very good linearity if we do the digital DFE algorithms properly. And also talking about different frequencies, FR2 and FR2 not only requires the hardware, but also it requires the system level solutions, including the processor and software and highly how you packaging the FR2 beamformer and the UDC converters. So pSemi and Murata together has in the past demonstrated in different venues the practical use of developed FR2 solutions. So not only the active components are important, but also the antennas and passive components also becoming more and more important as we move to the new frequency and higher frequency due to the wide bandwidth requirement. So this chart basically compares the popular or dominating filter solutions. So on this corner, it basically says X bars solutions from a Murata company, Resonant. It has a unique advantage when we move to the higher frequency and handling the high bandwidth of the signals. So what is the XBAR solution? XBAR basically, it combines the benefits, the merits between the SAW filter and the FBAR filter, becomes the XBAR filter. The feature including the piezoelectric single crystal, because therefore it has a relatively easy fabrication because the excitation is performed by the in the digital transducer, and the vibration mode, however, is also a Ball filter. So therefore, it can also offer the much wider bandwidth of the fractional bandwidth in the range of 15 to 20% at a higher frequency. So forward-looking and the summary of the FR3 development, and so the integration, the industry has moved from the past 3G to 4G and even to current 5G. The integrated solution with a wider bandwidth, higher efficiency, higher linearity solution for both base station and the front end has been the key trend. Because if we can do the integration, it offers a much smaller footprint, a lower cost, and more energy efficient solutions for both base station and user UEs. So therefore, we predict towards future integration is going to be the following trends. To summarize this webinars, we have went through the spectrum and the technology development trends overlook, and also the implementation challenge for the new beyond 5G and 5G advanced and 6G. We realized also further improving the power efficiency and extending the R front-end functionalities and the integrations remains a key concern. And we have also reviewed the innovative solution for both handset and the base station. These are still being researched globally, but this will further enable a sustainable world if we do the things right. And the FR3 and the 6G certainly will demand a unique solution for beamforming given the spectrum characteristics. And we also, especially on the base station side, further increase active antenna channel numbers and the array numbers of antennas will lead to a more extremely massive MIMO implementations, and will be a key enabling technologies for FR3 applications. So if you are interested, I would suggest you to look at this Murata website, and this basically highlights our visions and our innovations, not only at the communication side, but also towards the Sonai project, meaning getting prepared for the upcoming 6G. Innovation and communications, we all know, as key technologies which are enabling the future of connected world for all of us. With this, I thank you time and attention for the webinar today. With that, I hand over to the host. Thank you.
All right, so we have one question. We have, what is IDT? So it's in relationship to the SAW technology as well as XBAR.
Yeah, IDT stands for interdigital transducer. Let me go back to the slides. Okay. So basically, if you visit the website from Resonant, you can also get more information on the technology introduction. So if you see the SAW filters, they are SAW meaning surface acoustic wave, where the IDT their surface they are basically relying on interdigital transducer as an electrode to excite the wave, the acoustic wave. And on the bulk part, for example, as a F-bar, is a bulk acoustic wave. That means it relies on the bulk wave to do the filtering characteristics, but they each has its unique challenge moving to higher frequency, as we discussed in these slides. So even the SAW filter is preliminarily with limited up to the mid-high band, and however, it becomes quite a challenge if you go to the higher frequency. But by combining the unique, the relatively easy fabrication of the SAW and the high frequency and higher bandwidth of both, and we use a new technology. I cannot share too much on the IP side, but the benefits of XBAR is able to combine the marriage of these both technologies, offering the widest acoustic filter solution in terms of frequency fractional bandwidth of the signal, which is the key demand for the FR3 and the Wi-Fi applications. Thank you. Other question?
Yeah, we have another question. How long will it take to implement AI and ML-based spectrum sharing? To some extent, that's already starting. Again, it depends on the complexity of the model that's being defined, the overall system. So CBRS is already working with some level of overall spectrum control, but it's pretty limited. I do expect this to be iterative, and we'll see increasing capability over time. Another question is, what's the projected timing for the three portions of the WRC27 spectrum? So we had the 4.4, 7.1, and 14.8. Actually, the 4.4, depending on where you are, it's already been defined by 3GPP in the sense that band N79 covers this frequency range, or at least a portion of it. And then as we look at 7.1, I think that's going to be more challenging because of the incumbents that exist. And it is new to 3GPP. And then finally, 14.8, that's very much, I would say, new space for both ITUR as well as the IMT use cases. So if I were to put timing on it, I would say the 4.4 is now, and it really depends on local regulations. And 7.1, that's probably going to be 3 to 4 years. And then 14.8, it's probably going to align with what's been discussed for 6G, which is roughly a 2030 timeframe. All right, a couple other questions. How is pSemi trying to differentiate in the market against competitors like Broadcom, Qorvo, or Skyworks? Interesting question. I think we'll defer that until our marketing team wants to respond to that. We'll move on to another AI question. In case of AI ML-based spectrum sharing, do we need a wideband transceiver? I think what we're seeing presently in the handset would be indicative of what the capability is. It's much more what sensing, and then what do you do with the information that you receive? So more real-time measurements within the handset, as well as feeding that back to the network, as well as perhaps some autonomous decisions that the UE that then relays back to the network what it would like to do. So there are some discussions along that. It depends on, again, the model definition. I think the description is one-sided versus two-sided models of how that behaves. But I think what we presently have in the handset is sufficient and will be defined by basic capability to support the new bands coming on, 7.1, 14.8. And in general, I would say that we're seeing the capability going to higher bandwidths, overall bandwidth, meaning the full capability of a transceiver, but the channel bandwidth being more in the 100 to 200 megahertz range. Yeah, go ahead, Rui.
Yeah, I agree. I saw some other questions regarding the compound semiconductor and SOI silicon, comparing the gas and GaN from the audience. Let me take that one. So certainly, as I mentioned, one of the key features of moving to FR3 band is you would need massive MIMO, not only conventional massive MIMO, but further extremely increased highly integrated massive MIMO. People starting calling giga MIMO or extremely minimal. So that would actually implement the significantly increased number of ATR counts. And in my view, the SOI-based or silicon-based solutions would be offer a better benefits in terms of highly integration and in terms of the power levels, due to the fact that you have much higher increased number of antenna elements. The absolute power required from each active channels is also within the reach of what the silicon can offer. So given this integration and benefits and compared with the 3.5 or compound semiconductor, I think SOI and silicon would offer a much better attractiveness at this FR3 new frequency. Thanks for the question. Other questions? I cannot see the window if Peter or somebody can read.
Yeah, there's another question regarding basically FR2. Why is there no interest on the millimeter wave system deployment? And I think what we're seeing is that because of the range constraints at the higher frequency, that deployment is generally in very dense, high use user scenarios. So that's one of the main reasons why. And then in sort of going back to the WRC 27 question, what is the frequency band most probable to be deployed in the near future? So we have N104, which is the 6.4 to 7.1 gigahertz that's actively being worked on now in terms of getting it defined and deployed. Other bands that are being discussed, as I mentioned, the 7.1 is probably out 3 to 4 years. Closer in might be like a low 3 gigahertz for the US that is separate from ITU and not included in WRC. So that may move along fairly quickly in the US. And then I think also China is probably going to be building out and expanding its use of the 6 gigahertz for its licensed access. And then I think the final question, does the type of piezo substrate used for SAW to BAW to XBAR change? Do we have answers on that, Rui?
I think, unfortunately, we cannot provide more details on this substrate. That there's some something we could not share. Yeah. Thank you.
All right. I think that's the questions that we have.
Yeah. So let's hand over to the host about the following logistic and the sharing of the slides or recording. Madison, you
Yes, thank you all so much for joining us today. We look forward to seeing you all at our next webinar. There will be a recording that's sent out tomorrow with the slides presented today. So I hope you all have a great day. Thank you so much.
Thank you.
Yes, thank you.